In this video, we'll be solving questions on reactor sizing. Then we have a question which says that a gas mixture consists of 50% A and 50% inert. At 10 atm, we have our pressure to be 10 atm and enters the reactor with a flow rate of 6 dm cube per second. That becomes our volumetric flow rate because this is in dm cube, which is a volume. So 6 dm cube per second at 300 degrees Fahrenheit, which in Kelvin gives us 422.2 Kelvin. The laboratory measurements given in the table below showed the chemical reaction rate as a function of conversion. The temperature was 300 degrees Fahrenheit, the total pressure was 10 atm, and the initial charge and a cumular mixture of A and B, sorry, of A and B, according to the reaction. A going into B plus. Now, because it is an molar mixture, then we are going to say that the mole ratio of A, the initial mole ratio of A entering the reactor was 0.5, and that of the inert also 0.5. And then we can given the conversion and then the rate. And they're asking us to find the volume needed to achieve 80% conversion, assuming a continuous stirred-tank reactor. So now I want to find the volume of the reactor to achieve this conversion here, 80%. They didn't give us the reactor, but then first question is saying that we should assume the CSTR. The first thing to do is that first have to know the design equation of a CSTR, which is your volume V equals FA naught X all over RE. So it means that our X here, the conversion we need, which is 80%. Our RE here counts the rate the reacting at that 80% conversion. And then our FA naught is our initial molar flow rate. We know this, and then we are left with this. We have to find our initial molar flow rate. FA naught is equal to initial concentration of A times initial volumetric flow. So we need to find CA naught too. And then our CA naught here equal to YA naught, which is initial mole fraction A multiplied by the total inlet concentration. Then our total inlet concentration can be written as, because it's a gas mixture, so we can have P over RT. This becomes our total concentration. So therefore, our CA naught here becomes YA naught times P all over RT. Our YA naught is 0.5. Our pressure is 10 atm, but then in terms of kilopascal, it's 1013 kilopascal. And then our R, if your pressure is in kilopascal, then your R becomes 8.314. So our R becomes 8.314. And then our temperature here should be in Kelvin, which is 422.2 Kelvin. So we get our initial concentration of A to be 0.5 times 1013 all over 8.314 times 422.2. We get our initial concentration of A entering the reactor to 0.144 mole per decimeter cube. But then we need FA naught. So our FA naught here becomes 0.144 times our V naught, which is our initial volumetric flow rate. Initially, the volumetric flow rate was 6 dm cube per second, 2 times 6. We need FA naught, not FA. So, but then if you had needed FA, then we know that FA is supposed to be CA times B. Then our V here wouldn't be equal to V naught because this is a gas phase reaction, not a liquid phase reaction. So 0.144 times 6, and that gives us 0.864. mole per second, because this is in mole per dm cube and this is dm cube per second, so they cancel out. We have our Fe naught to be 0.864 mole per second. Now to find our mole, we know that the design equation for a CSTR is just Fe naught x all over. Our Fe naught has been given. So we found our Fe naught to be 0.864. And then our convention is 80%, but that's what we want. And our Re here is given as 0.00125. The Re to achieve an 80% conversion, 0.00125. And then we can find our volume to be 0.864 times 0.8, all divided by 0.001. So then we get 552.96 dm cube. Now this becomes the volume of the CSTR needed to achieve the 80% conversion. Now the second part is that we should assume a PFR. So the first thing to do is again write the design equation of a PFR, which is a plug flow reactor. With the PFR, the design equation is Fa naught dx dV should be equal to minus Re. And then we need our volume. So dV becomes Fa naught dx all over minus R. And then we can find our V to be integral from 0 to x, because this is the x, of Fa naught dx all over Re. Our Fa naught is a constant, so you can bring it out. Then we are left with dx over minus Re. Now, because we have this to be our design equation, it can be easily inputted as we did for the CSTR. But you are looking at range of values from 0 to a certain conversion value. So if you want to find the 80% conversion, that is going to be our volume is supposed to be from 0 to 0.8. Fa naught comes out dx minus R. So that means I'm going to do integral of a numerical, and then there are approaches that we can use to do that. So the common ones we know is the 5-point quadrature rule. Or some other books too, you can use the Simpson's 1/3 rule and then the 1/8 rule. And then you're looking at the 5-point quadrature rule. That will give us the evaluation of this point. So we can have our V to be Fa naught integral from 0 to 0.8 dx over minus Rb. The whole of this is what we are going to use the numerical integration, which is the 5-point quadrature. So the 5-point quadrature, we are going to get our V, or let's say the evaluation of this whole thing, the integral part, 0 to 0.8 dx minus Re is giving us. So we need our step divided by 3, everything multiplied by 1 over minus Ra at x equals 0. So first of all, we have to know how we want to divide, how we want to split, or the data point that we want. What's been given here was from 0.0 to 0.85. From 0.0 to 0.85. And then we want an 80% conversion. So it depends on what we want to do. If we want to do the 5-point quadrature rule, it means that we are going to select 5 points out of the many points that we have here. So how do we select it? We need to find the step. And then the step or the change will help us get what we want. So our step here, changing x, will now be from what we want, 0.8 or 0 to 0.8. Right? That's what we want. So that becomes 0.8 minus 0 all over. Because it's in the 5 point, that means we need 5 data sets for this. All over 5 minus 1. Now anytime we want to divide a set of data into like n number of components, then we are going to divide, when we want to find the step, we are going to divide it by n minus 1. So this gives us 0.8 divided by 4, and that will be 0.2. So that means our step is 0.2. So our volume now becomes FA naught multiplied by, so the whole of this times change in x, which is our step, 0.2 divided by 3 here. So this is part of the formula, right? The 5-point quadrature rule its own self is just changing x over multiplied by 1 over minus r, blah blah blah, so you get to the fifth term you want. Everything multiplied by 1 over minus ra. Now, because we are starting from 0 and then the step is 0.2, so at x equals 0 plus, and this is the formula for the 5-point quadrature. The ones on top here are constant, minus ra. Now x equals 0.2 because you are looking at a 0.2 step, plus, then the next one is 2 all over minus ra, x equals 0.4, plus 4 over minus ra, x equals 0.6. Then finally plus 1 over minus ra, x equals 0.8. Now, so getting this 1, 2, 3, 4, 5. So that means we have our 5 data. Our V becomes our F units. We had it to be 0.864, and then 0.2 over 3. We just have to evaluate at x equals 0. What is the value of 1 over Ra? Or we can just put it here as 1 over, then Ra is 0.0053, which is at x equals 0, plus 4 over, at 0.2, we are going to have 0.0050 plus 2 all over, at x equals 0.4, we are going to have 0.004 plus, at x plus 4 over, at conversion of 60%, which is 0.3, we are going to have 0.002 plus, let me continue here, plus at 1 over x at 80%, 0.001. So then we have to just input this into our calculator. Our volume now becomes 0.864 times 0.2 over multiplied by 1 over 0.0053 plus 4 over 0.005 plus 2 over 0.004 plus 4 over 0.0025 plus 1 over 0.00125. Now we get our volume to be 223.99 cm cube. We realize that to get certain conversion of E, which is the 80% conversion, when you are using a PFR, you need a smaller volume as compared to using a CSTR. So that will be all for now.